Chapter 2. Preparing for Space. In the summer of 1961, the United States was pushing hard to strengthen its position in the exploration of space and the near planets. The National Aeronautics and Space Administration was planning two projects, both to be launched by an Atlas booster and a Centaur high-energy second stage capable of a much better performance than that available from earlier vehicles. The Mariner program had two goals. Mariner A was ticketed for Venus and Mariner B was scheduled to go to Mars. Caltech's Jet Propulsion Laboratory had management responsibility under NASA for both projects. These spacecraft were both to be in the 1,000 to 1,250 pound class. Launch operations for the two planets were to be best during 1962 to 1964 period, and the new second stage booster known as Centaur was expected to be ready for these operations. But trouble was developing for NASA's planners. By August 1961, it had become apparent that the Centaur would not be flying in time to take advantage of the 1962 third quarter firing period, when Venus would approach inferior conjunction with the Earth. JPL studied the problem and advised NASA that a proposed lightweight hybrid spacecraft, combining certain design features of Ranger 3, a lunar spacecraft, and Mariner A, could be launched to Venus in 1962 aboard a lower-powered Atlas Agena bead launch vehicle. The proposed spacecraft would be called Mariner R and was to weigh about 460 pounds and carry 25 pounds of scientific instruments, later increased to 40 pounds. The restart capability of Agena was to be used in a 98 statute-mile parking orbit. The orbit was later raised to 115 statute miles, and the spacecraft weight was reduced to about 447 pounds. Two spacecraft would be launched one after the other from the same pad, within a launch period extending over 56 days, from July to September 1962. The minimum launch separation between the two spacecraft would be 21 days. As a result of JPL recommendations, NASA cancelled Mariner A in September 1961, and assigned JPL to manage a Mariner R project to fly two spacecraft, Mariner 1 and 2, to the vicinity of Venus in 1962. Scientific measurements were to be made in interplanetary space and in the immediate environs of the planet, which would also be surveyed in an attempt to determine the characteristics of its atmosphere and surface. Scientific and engineering data would also be transmitted from the spacecraft to the Earth while it was in transit and during the encounter with Venus. Scientists and engineers were now faced with an arduous task. Within an 11-month period on a schedule that could tolerate no delays, two spacecraft had to be designed, developed, assembled, tested and launched. In order to meet the schedule, tested flight assemblies and instruments would have to be in the Pasadena Assembly Facility by mid-January 1962, just 4 months after the start of the project. Probably no other major space project of similar scope had ever been planned on such a demanding schedule. With the shipment of equipment to Atlantic Missile Range, AMR, scheduled for 9.5 months after inception of the project, management and design teams went all out on a true crash effort. Quick decisions had to be made. A workable design had to be agreed upon very early, and once established, the major schedule objectives could not be changed. Certain design modifications and manufacturing changes in the Atlas Agena launch vehicle were also necessary. Wherever possible, Ranger design technology had to be used in the new spacecraft and adopted to the requirements of a planetary probe. Other necessary tasks included trajectory calculation, arrangements for launch, spaceflight and tracking operations, and coordination of AMR range support. Following NASA's September 1961 decision to go ahead with the Mariner R project, JPL's director, Dr. William H. Pickering, called on his seasoned team of scientists and engineers under Robert J. Parks, planetary program director. Jack N. James was appointed as project manager for Mariner R, assisted by W.A. Collier. Dan Schneiderman was appointed spacecraft system manager, and Dr. Eberhard Rechtin headed the space tracking program, with supervision of the Deep Space Instrumentation Facility, DSIF, operations under Dr. Nichols Renzetti. The Mariner spaceflight operations were directed by Marshall S. Johnson. A problem in celestial dynamics. In order to send Mariner close enough to Venus for its instruments to gather significant data, scientists had to solve aiming and guidance problems of unprecedented magnitude and complexity. The 447-pound spacecraft had to be catapulted from a launching platform moving around the Sun at 66,600 miles per hour, and aimed so precisely that it would intercept a planet moving 78,300 miles per hour, or 11,700 miles per hour faster than the Earth, at a point in space and time some 180.2 million miles away and 109 days later, with only one chance to correct the trajectory by a planned mid-course maneuver. And the interception had to be so accurate that the spacecraft would pass Venus within 8,000 to 40,000 miles. The chance of impacting the planet could not exceed 1 in 1,000, because Mariner was not sterilized and might contaminate Venus. Also, much more data could be gathered on a near-miss flight path than on impact. Furthermore, at encounter in the target area, the spacecraft had to be so positioned that it could communicate with Earth, see the Sun with its solar panels, and scan Venus at the proper angles. Along the way, Mariner had to be able to orient itself so that its solar panels were facing or locked onto the Sun in order to generate its own power. Acquire and maintain aerial orientation to the Earth, correct its attitude constantly to hold Earth and the Sun lock, receive, store and execute commands to alter its course for a closer approach to Venus, and communicate its findings to Earth with only 3 watts of radiated power over such distances never before spanned. Early in the program, it had been decided that 2 spacecraft would be launched towards Venus. Only 56 days were available for both launchings, and the planet would not be close enough again for 19 months, the period of inferior conjunctions or the planet's closest approach to the Earth. On any one of these days, a maximum of 2 hours could be used for getting the vehicles off the launch pad. In addition, the mariners would have to leave the Earth in a direction opposite to that of the Earth's direction of orbital revolution around the Sun. This flight path was necessary so that the spacecraft could then fall in towards the Sun and intercept Venus, catching and passing the Earth along the way about 65 days and 11.5 million miles out. This feat of celestial navigation had to be performed while passing through the hostile environment of interplanetary space, where the probe might be subjected to solar winds, charged particles, travelling at velocities of up to 500 miles per second, intense bombardment from cosmic radiation, charged protons and alpha particles moving perhaps 1.5 million miles per hour, radiated heat that might raise the spacecraft temperatures to unknown values, and the unknown dangers from cosmic dust, meteorites, and other miscellaneous space debris. In flight, each spacecraft would have to perform more than 90,000 measurements per day, reporting back to the Earth on 52 engineering readings and changes in interplanetary magnetic fields, the density and distribution of charged particles and cosmic dust, and the intensity and velocity of low-energy protons streaming out of the Sun. At its closest approach to Venus, the spacecraft instruments would be required to scan the planet during a brief 35-minute encounter to gather data that would enable Earth scientists to determine the temperature and structure of the atmosphere and the surface, and to process and transmit that data back to Earth. The Organisation. Flying Mariner to Venus was a team effort made possible through the combined resources of several United States governmental organisations and their contractors, science and industry. The success of the Mariner project resulted primarily from their overall direction and management of the National Aeronautics and Space Administration and the Jet Propulsion Laboratory, and the production and launch capabilities of the vehicle builders and the Air Force. Several organisations bore the major responsibility: NASA Headquarters, JPL, NASA's Marshall Space Flight Center and Launch Operations Center, Aeronautics Division of General Dynamics, and Lockheed Missiles and Space Company. NASA. For science. The National Aeronautics and Space Administration was an outgrowth of the participation of the United States in the International Geophysical Year program and of the nation's space effort, revitalized following Russia's successful orbiting of Sputnik 1 in 1957. Under the terms of the law which created NASA, It is a federal agency dedicated to carrying out activities in space, devoted to peaceful purposes for the benefit of all mankind. NASA is charged to preserve the role of the nation as a leader in the aeronautical and space sciences and technology, and to utilize effectively the science and engineering resources of the United States in accomplishing these goals. Activities associated with military operations in space and the development of weapon systems are specifically assigned to the Defense Department. In November 1957, before the creation of NASA, President Eisenhower had established a scientific advisory committee to determine the national objectives and requirements in space, and to establish the basic framework within which science, industry, and the academic community could best support these objectives. The committee submitted a report to the President in March 1958, recommending creation of a civil agency to conduct the national space programs. The recommendation, endorsed by the President, was submitted to Congress on April 2, 1958. The National Aeronautics and Space Act of 1958 was passed and became law in July 1958. NASA was officially established on October 1, 1958, and Dr. T. Keith Glennon, President of Case Institutes of Technology, was appointed as the first administrator. The facilities and personnel of the National Advisory Committee for Aeronautics, NACA, were transferred to form the nucleus of the new NASA agency. NACA had performed important and significant research in aeronautics, wind tunnel technology, and aerodynamics since 1915, including a series of experimental rocket research aircraft that culminated in the X-15. It was natural that it be expanded to include space operations. Among the NACA centers transferred to NASA were the Langley Research Center at Hampton, Virginia, Lewis Research Center, Cleveland, Ohio, Ames Research Center, Moffett Field, California, Flight Research Center, Edwards, California, and the Rocket Launch Facility at Wallops Island, Virginia. Those personnel of the Naval Research Laboratory who had been working on Project Vanguard were also transferred to NASA, as was the project. These personnel are now part of the Goddard Space Flight Center at Greenbelt, Maryland. The October 1958 transfers also included a number of space projects of the Advanced Research Projects Agency of the Defense Department. In a December 1958 executive order, the President assigned the former Army facilities of the Jet Propulsion Laboratory at Pasadena, California, to NASA. At the same time, the group working under Dr. Werner von Braun at the Army Ballistic Missile Agency, commanded by Major General John B. Medaris, was made responsive to NASA requirements. On July 1, 1960, the George C. Marshall Space Flight Center, MSFC, was organized at Huntsville under von Braun's direction. The former Development Operations Division of ABMA formed the nucleus of the new center. The MSFC mission was to procure and to supervise the adaptation of launch vehicles for NASA space missions, including Atlas, Thor, and Agena. Marshall is directly responsible for the design and development of advanced high-thrust booster vehicles such as the Saturn C-1 and C-5 and the Nova. An agency to conduct NASA affairs at Cape Canaveral was formed within the MSFC on July 1, 1960. Known then as the Launch Operations Directorate, or LOD, it was directed by Dr. Kurt H. DeBus. LOD became independent of Marshall in March 1962, when it was redesignated the Launch Operations Center, LOC, reporting directly to the Office of Manned Spaceflight. This separation resulted largely because the activities at AMR were becoming more operational in character and less orientated towards research and development. LOC handles such functions for NASA as the scheduling of launch dates and liaison with the Atlantic Missile Range for support activities. The Centre will have the responsibility in the field for assembly, checkout, and launch of the Saturn and Nova boosters. Following the election of President Kennedy in 1961, James E. Webb replaced Dr. Glennon as administrator of NASA. Shortly after, a new national goal was announced, placing a man on the Moon and returning him safely to the Earth in this decade. Meanwhile, JPL had been assigned responsibility for unmanned exploration of the Moon, the planets, and the interplanetary space, and thus was charged with supporting the NASA manned flight program through these activities. In less than 5 years, NASA grew to include 8 flight and research centres and about 21,000 technical and management personnel. Within NASA, Dr. Abe Silverstein's Office of Space Flight Programs was responsible for the Mariner R project, which was directly assigned to Ed Courtwright, Director of Lunar and Planetary Programs, and Fred Cockendorfer, who is NASA's Program Chief for Mariner. A subsequent reorganisation placed responsibility under Dr. Homer Newell's Office of Space Sciences, and Orrin Nix became Director of Lunar and Planetary Programs. JPL, JATO to Mariner. The Jet Propulsion Laboratory, staffed and operated for NASA by California Institute of Technology, had long been active in research and development in the fields of missiles, rockets, and space-associated sciences. The first government-sponsored rocket research group in the United States, JPL, had originated on the Caltech campus in 1939, an outgrowth of the Guggenheim Aeronautical Laboratories, then headed by celebrated aerodynamicist Dr. Theodore van Karman. Von Karman and his associates moved their operation to a remote spot at the foot of the San Gabriel Mountains, and, working from this base in 1941, the Pioneer Group developed the first successful jet-assisted aircraft takeoff, JATO, units for the Army Air Force. The laboratory began a long association with the Army Ordnance Corps in 1944, when a Private A test rocket was developed. In retrospect, it is now recognized that the Private A was the first U.S. surface-to-surface solid propellant rocket. Its range was 10 miles. JPL's WAC Corporal rocket set a U.S. high-altitude record of 43.5 miles in 1945. Mounted on a German V-2 as the bumper WAC, it achieved an altitude record of 250 miles in 1947. More important, this event was the first successful in-flight separation of a 2-stage rocket. The feasibility of space exploration had been proved. After the end of World War II, JPL research set the stage for high-energy solid propellant rockets. For the first time, the solid propellants, which contained both fuel and oxidizers, were cast in thin-walled cases. Techniques were then developed for bonding the propellants to the case, and burning radially outward from the central axis was achieved. Attention was then turned to increasing the energy of the propellants. By 1947, the Corporal E, a new liquid propellant research rocket, was being fired. JPL was asked to convert it into a tactical weapon in 1949. The Corporal E then became the first liquid propellant surface-to-surface guided missile developed by the United States or the Western Bloc of nations. Because of the need for higher mobility and increased firing rate, JPL later designed and developed the solid propellant Sergeant, the nation's first second-generation weapon system. This inertially guided missile was immune to electronic countermeasures by an enemy. Meanwhile, JPL scientists had pioneered in the development of electronic telemetering techniques, which permit an accurate monitoring of a system of performance while missiles are in flight. In 1944, Dr. William H. Pickering, a New Zealand-born and Caltech-trained physicist who had worked with Dr. Robert Millikan in cosmic ray research, had been placed in charge of the telemetering effort at JPL. Pickering became director of the laboratory in 1954. Following the launching of Sputnik 1, the Army JPL team, which had worked on the Jupiter-C missile to test nose cones, was assigned the responsibility for putting the first United States satellite into orbit as soon as possible. In just 83 days, a modified Jupiter-C launch vehicle was prepared, an instrumented payload was assembled, a network of space communication stations was established, and Explorer 1 was orbited on January 31, 1958. Explorer was an instrumented assembly developed by JPL and the State University of Iowa. It discovered the inner Van Allen radiation belt. Subsequently, JPL worked with the Army on other projects to explore space and to orbit satellites. Among these were Pioneer 3, which located the outer Van Allen belt, and Pioneer 4, the first U.S. space probe to reach Earth escape velocity and to perform a lunar flyby mission. General Dynamics. The Atlas. The launch vehicle for Mariner was an Atlas D booster, with an Agena B second stage. Historically, Atlas can be traced to October 1954, when the former Convair Corporation, later acquired by General Dynamics, was invited to submit proposals for research and development of 4 missile systems, including a 5,000-mile intercontinental weapon. In January of 1946, Convair assigned K.J. Bossart to begin study of 2 proposed types of 5,000-mile missiles. One jet-powered at subsonic speeds with wings for aerodynamic control. The other a supersonic ballistic wingless and bullet-like rocket-powered missile capable of operating outside the Earth's atmosphere. This was the beginning of Project MX-774, lineal ancestor of Atlas. After captive testing at San Diego in 1947, 3 of the experimental missiles were test launched at White Sands Proving Ground in New Mexico. The first flight failed at 6,200 feet after a premature engine burnout. In 1947, the Air Force shelved the MX-774 project. However, this brief program had proved the feasibility of 3 concepts later used in Atlas: swiveling engines for directional control, lightweight pressurized airframe structures, and separatable nose cones. The North Korean War stimulated the ICBM concept, and in 1951 a new MX-1593 contract was awarded to Convair to study ballistic and glide rockets. By September 1951, Convair was proposing a ballistic missile that would incorporate some of the features of the MX-774 design. A plan for an accelerated program was presented to the Air Force in 1953. After a year of study, a full go-ahead for the project, now called Atlas, was given in January 1955. The unit handling the Atlas program was set up as Convair Astronautics, with J.R. Dempsey as president, on March 1, 1957. The first Atlas test flight in June of 1957 ended in destruction of the missile when it went out of control. Following another abortive attempt, the first successful flight of an Atlas missile was made from Cape Canaveral on December 17, 1957. The Atlas program was in full swing by 1958, when 14 test missions were flown. The entire missile was orbited in December 1958 as Project SCORE. It carried the voice of President Eisenhower as a Christmas message to the world. The Atlas missile system was accepted for field operations by the Air Force in 1958. Also in 1958, an Atlas achieved a new distance record, flying more than 9,000 miles down the Atlantic missile range, where it landed in the Indian Ocean off the South African coast. Atlas has been modified for use by NASA as a space vehicle booster, known as the Atlas D. It has launched lunar probes, communications and scientific Earth satellites, and manned vehicles into space. Lockheed Agena B. The Lockheed Agena B second stage vehicle was mounted on top of the Atlas booster in the launch of the Mariner spacecraft. The U.S. Air Force had first asked Lockheed Missiles and Space Division, headed by L.E. Root, to work on an advanced orbital vehicle for both military and scientific applications in 1956. On October 29th of that year, Lockheed was appointed prime weapon system contractor on the new Agena project under the Air Force Ballistic Missile Division. In order to speed the program, the Thor missile was used as the booster stage for the early Agena flights. The Atlas was also utilized in later operations. In August 1957, the Air Force recommended that the program be accelerated as much as possible. After Russia orbited Sputnik 1 in October of 1957, a further speed-up was ordered. The first of the Agena Discoverer series was launched into orbit on February 28, 1959, with the Thor missile as the booster. The first restart in orbit occurred on February 18, 1961, when the new Agena B configuration was used to put the Discoverer 21 into orbit. All of the NASA missions using Agena, beginning with Ranger 1 in August 1961, have been flown with the B model. Agena holds several orbiting records for U.S. vehicles. The first water recovery followed the 17 orbits of Discoverer 13 on August 11, 1960. The first air recovery of a capsule from orbit occurred with Discoverer 14 on August 18, 1960. In all, a total of 11 capsules were recovered from orbit, 7 in the air and 4 from the sea.